Okay, so let us look at the derivation of the first principle of thermodynamics. So in many textbooks, probably you will find out that they call this the first law of thermodynamics. But personally, I think the word principle is more appropriate because the laws in physics, for example, Newton's law is a law, means that it cannot be derived or proved. However, a principle is something that is derived from an existing law, which is what actually we're going to be doing today. So for the first principle of thermodynamics, so we say thermodynamics has the word dynamics. So the definition of dynamics is what? Is summation of forces equals to ma. So this is the starting equation. We know that we can rewrite this as summation of forces equal to m dv dt. Then, using the chain rule, we can do m dv dr, where dr is a position vector, times dr dt, where dr dt from dynamics, you should remember that this is the velocity. So basically that means that we have summation of forces equal to m v dv dr. So now you should remember from your differential equation class that in order to solve one equation, what you need to do is to separate the variables. So on this side, you see you have the velocity variable, F would be the forces, constant forces, and this is dr. So what we can do is move the dr variable to the left-hand side so that we just have the velocity variable on the right-hand side. Once you separate the variables, now you are capable of integrate. So if you leave the left-hand side untouched, you will have what? And let's say we integrate between an initial and final velocity. You have on the right-hand side 1/2 mv final square minus 1/2 mv initial square. Okay? And here notice that we went from a vector equation to a scalar quantity. The reason is because when you do the scalar product or the dot product of two vectors, you get a scalar quantity. So that equation here you have probably seen it before, is what is known as the work and energy equation. So on this equation, this term over here is known as the work, and the right hand side terms is the change in kinetic energy. All right. So now, for the sake of simplicity, let me just rewrite this as summation of forces dr equal to change in kinetic energy. Okay. Now, this is work. So now this term, we're going to break it probably in 3 components. So maybe let's start by the easiest one. Let's say work done by friction forces. So when you have friction, let's say you rub one surface against the other one multiple times, what are you going to observe? You're going to observe that you're going to create heat. That's actually one way to start the fire. So you might not be able to calculate exactly what is the amount of work created by the friction force, but you know that the amount of work created by the friction force will generate heat, and that heat should be proportional to the amount of work. So basically the work done by the friction forces will be equal to Q. Then over here we're going to look at work done by all other forces, and this one we're just going to call it the general work. You will see later on, in most cases, will be the work done by the pressure, and then the last case will be the work done by conservative forces. Okay, so without getting into too many details about the conservative forces, I'm just going to do a very quick derivation for 2 types of forces that you are familiar with. So the first one will actually be the weight. So let's see, if we do a little figure over here, so let's say you have this object over here, you have a reference frame, X, Y, and basically you see there's a change in height over here. Alright, so let's say it will be H. So if we look at what is the work done by the weight, which is the expression summation of forces dr, in our case, what is the value of the weight force? We know is equal to mg. So this will be equal to, I leave some space over here, will be mg, and dr here is just the direction of the movement, so in our case will be dy. Okay, what's important over here is that you see that the weight goes against the positive y, so actually this becomes negative, and if you look at the figure you can say that the change in height is only between 0 and h. So basically at the end we get that the work done by the weight is equal to minus mgh. And maybe you recognize that this is actually the potential energy done by the weight. Okay, so now if we look very quick at another case, let's say spring force. So again, let's do a quick figure. We have a spring. Let's say you apply a force. You know the spring will always create a force against the natural force, which is equal to kx. Okay, so in our case, again, we do the same thing. What would be the work done by the spring force? Summation of forces dr equal to value of the force of the spring is kx. Will always be on the opposite direction of the force, or if you want, if this is positive, this will be negative, and in this time dr will be dx. So after integration you will see that the work done by the spring force is actually equal to minus 1/2 kx squared, which you might recognize as the potential energy of a spring. So basically we can say that the work done by conservative forces yield to the potential energies. Okay, so just to simplify, let's say summation of forces dr done by the conservative forces would just be equal to the change in potential energy, and you notice the negative value. Okay, so if we go back to our initial equation, this one over here, we could just rewrite this one. So this equation will become what? So the equation summation of forces dr equal to change in kinetic energy will become what? So the first term, let's say the work done by all the friction forces will be Q. Okay, then the work done by all the other forces will be W. The work done by the conservative forces, we just say will be equal to minus delta PE, and this should be equal to the change in kinetic energy. So if we just rearrange this equation, we're going to have that heat plus work equal to the change in kinetic energy plus the change in potential energy. Okay, we are almost done with the derivation of the first principle. I just need to add one more thing and then give a final comment. So on the equation here we have Q plus work equal change in kinetic energy plus change in potential energy. And I'm going to add here one extra term, which is generally denoted by delta U. And the delta U over here is the change in internal energy, which basically includes all the internal changes in energy. So for example, if you have water going from the liquid state to the solid state ice, you know that the molecular structure of the water liquid is not the same as the one of the ice. And one example would be the snowflakes. Okay, so in order to change the orientation of the molecule or the atoms, some energy is required. Okay, so to go from one state to the other, there's some internal energy that need to be used, and this is the term considering all this microscopic interaction. Okay, and that's the change in internal energy. So at the end, we can just summarize that equation saying that Q plus work equal to the change in energies. So I didn't go into too many details, but basically this is the derivation of the first principle of thermodynamics. Okay, so now one final comment, but it's important. Before I do the comment, I just give you here what would be the sign convention for this. So for this equation, if this is your system, the amount of heat going in will be positive, the amount of work done on the system will be positive, the amount of heat coming out will be negative, and the amount of work done by the system will be negative. Okay, so this is an important here, a note, so comment. In some textbooks, the first principle of thermodynamics is written as heat minus work equal to the change in heat. Okay, and just because your textbook uses this notation, this is the one I'm going to use from now on. Okay, so I'm going to tell you why they do this. It's very easy to understand. So basically, for this new system, I mean, it's the same system, but you will see the Q is unchanged. So Q going in will be positive, Q coming out will be negative. But now the change comes in what the work coming in will be negative, and the work coming out will be positive. So really, the one that is mathematically correct is this one, but this one is a little bit easier sometimes to understand, because basically what we're trying to do here is to study the amount of work or energy produced by different engines. So it's easier to understand, let's say, that if you put that amount of energy into a system, you're going to get that amount of work. Okay, so basically, let's say this is 0 here, you will have amount of work put on the system equal to the amount of work you get out of the system. However, if you use this notation, you will say the amount of heat put in the system will be equal to it will mean the same thing, but this time the amount of work done by the system will be a negative value instead of a positive value in this case. Okay, so that's it, and on the next video I'm going to use again the same. At the beginning I'm going to use these two equations, and I will give the definition for the work done by the pressure. See you in a few minutes.